Are you all able to share, see the screen?
Yes,
So
sir.
you do. Okay. So yeah, week one I'll be uploading uh, uh, tomorrow or day after tomorrow. Uh, let's start with the second week content. What have you mm, read in the past week? Can anyone summarize? What are the topics that you have gone through? Anyone? Just merely mention the topics. That's it. Just- just- Anyone who could summarize the topics, just mention the topic. That's it. Mm.
The UGT
Yeah.
as an amplifier and
Mhm.
UGT small signal circuit model. And we also did the Ebers model.
For the BJT, right?
Yes, sir.
Okay. So let me introduce to. I mean, I want you to go through few different questions. Okay. I guess the screen is basically. It should be now, right? Okay. So what I plan to do is let me go through some prerequisites quickly. It is expected that you would have gone through the previous lectures that were uh, taught by the instructor on the course webpage, and it's also expected that you would have, uh, I mean, attempted the assignments before attending this session. So, was the week two assignment already posted? It should have been, right? Okay, I'll assume yes. Then. So, please make sure that you would have muted the microphone all the time unless you're asked not to. And if you have questions at any point of time, feel free to raise them. And after each problem, you would be given some time to ask your doubt. We can have a discussion basically after every problem. And uh, at last, we'll have a 10-minute general discussion. Okay. So it's expected that you would have a scientific calculator handy during the session because that would help with the calculations. So with that, let's start now. Okay, so this is the first question. So it goes like this. If we were to compare the energy diagrams for three pieces of semiconducting material, right? So this is your N type, right? This is your P type, and this is your N type, right? Uh, Say we have them side by side like this. Okay. and presence of dopants in these semiconductor materials, right? Because there would be uh, donor atoms here, acceptor ions here, and donor atoms here, right? It would, I mean, alter the Fermi levels, right? I mean, don't expect the Fermi level to be at the same planes as you would for an intrinsic semiconductor, right? This is the all of them are extrinsic. Is this clear? Uh, Please do at least respond yes, no. I mean, if you understand, giving me feedback will help me. Okay. So now what we are asked to do is we are supposed to draw energy band diagram showing the equilibrium state of the three pieces after they are being joined together. Okay. So how should we proceed on this one? Yes, anyone? So this would be equilibrium after we join them, right? So what would happen to electrons? Electrons would diffuse from N region to P region, right? And what about holes? They would basically diffuse from P region to N, right? Likewise, I mean, electrons would diffuse from N to P, N to P, and holes would diffuse from P to N, P to N. Okay, now this charge transfer would leave behind, or I should say, uncover ionized donors in the N region uh, and ionized acceptors in the P region near the junctions. Right? This is a junction. If I were to make a diagram, it looks something like this. Right? Suppose I join them. Right? So this is junction, and this is junction. There would be a depletion region formed, which I'm sure you all would be aware of. Right? Why would this depletion region be formed? Because what should I say? Dopant ions they would be uncovered, right? So on this side we would have donor ion side, and this one, and on this side I would have this one. Okay, and likewise for this one as well. So this is my N type. This is my P type. This is my N type. Right, I would have a similar situation here. With the acceptor. Um, right. I guess I this was NPN, right? My electrons diffuse from N to P, right? So I mean we will have sector ions on this side. Yeah, that is what we should hold on. So we'll have something like this. On N side, we have donor ions. Right? So when you uncover them, when electron goes from this to this, it will leave behind a positive ion, right? Positive donor ion. Likewise, we'll acceptor ion because holes would have diffused from this to this. Right? Similar situation here as well. We'll have donor ions on this side and acceptor ions on this. Is this clear? Right. Now, what would happen to the Fermi level? Right. If I individually draw them, it would look something like this. Right. For N side, this is my which band? Conduction and valence bands, respectively. Right. Where would be the Fermi level? Will it be close to the conduction band or will it be close to the valence band for N type? Interact because, oh, is my voice not clear? Let me know if you are able to hear me. Hello. I hope my voice is clear. Okay. Now for this one, where would the Fermi level be? It would be close to this one, right? Close to the conduction band. Likewise, for P type, where would the Fermi level be? Close to the valence band, right? This is where my EF would be. And what about this last one? N type again. I think this would be a copy of this one. Right? Can basically copy this. Copy, paste it. Okay, done. So now the question is, what will happen after the equilibrium? Right? At equilibrium, let me introduce a page. Do this on new page. Okay, so page should be like this. Yeah. So now at equilibrium, my Fermi level would be constant, right? This is my mu. Now, so my conduction and valence band would, uh, bend in the following manner. Right? It should be somewhat like this. It should be PC was close to this one. Just a second, Adrian. For the interruption, I I got a call from coordinator. I mean, I need to share the link with him as well. Sorry for the inconvenience. Just um, yeah, share the link with him. Maybe other students can join us. Share it again. Screen. I hope it's visible now. So, how should our this band diagram look like? Note this, right? This would remain fixed here, right? So, my EC would be somewhat this, this, right? And then I need to join them. I would likewise have this as well. Uh, something. Why is this the case? Because this EG remains constant, right? Anywhere at any coordinate. This coordinate is XI position. So at any point, EG needs to be fixed. Yeah. Uh, can you mute yourself? Abhi, I'm talking to you. Can you mute yourself? Let me mute you. Okay. So yeah. So this one is EC. This one is EB, right? And this one is EF. So this would be EG, right? So that and even vacuum level would follow something similar. One, two, three, four. Say it starts from here. Goes like this. Getting a better idea. Why don't I just copy this? Paste it here. This is not there. Yeah, this is my E naught. This is EC, this is EV, this is EA. Fine. So what about this now? What is this? Electron affinity, right? Q car. This EG and what else? Hmm, what is this quantity from E naught to EF? That's your work function. Okay, and that although doesn't need to be constant, but this Q chi and EG they remain constant throughout physics. Okay, so and in fact your this E or like vacuum level, this conduction band level, and valence band level, they're in fact parallel to each other, right? At any point, they would be parallel to each other. So yeah, done with this one. Now let's move to the second one. Right. This is what the question had asked, right? We had to draw a new energy band diagram that showed the equilibrium state of the three pieces after being joined together. Now the second question. If this is your BGT function, I mean it's usually considered in terms of the currents, right? Relatively small current through one of the transistor's terminals, it exerts control over much larger current. Draw the directions of all the currents for these two transistors, one NPN and one PNP. Clearly identify which of the currents is doing the control and which of the currents is being controlled. Okay. Yes. So how should we proceed on this one? For the NPN case, this is IC, right? And this is IV and this is IE. Is this clear? Right. And which is the controlling current? This is the input, right? So this is the controlling current. And what is uh, which of the currents is getting control? Yes, anyone? I mean, you have studied BGT in depth, right? You have gone through the small signal models of BGT, the Ebermond's model of the BGT. But this is the one, right, that we use to control the BGT. Because unlike MOSFET, which is a voltage controlled current source, our BGT is what? Yeah, let's. I should have started with that question. what is BGT effectively? Your MOSFET, and please interact. I mean, I want you all to, I mean, one by one, obviously, but unmute and answer my questions. If you don't know, just tell me that you don't know, because it would save time, right? That's it. So your MOSFET is a voltage controlled current source. Is this fine? I mean, are you first of all aware of MOSFET? Has this been taught in any of the courses? I mean, in our introductory session, you guys did mention that most of you are from EC background, right? So has MOSFET been taught in the curriculum? No? Yes? Okay, yes. So do you agree that this MOSFET is a voltage controlled current source? Was that yes for VCCS or yes for what? Okay, I'll assume you all are saying that MOSFET is a voltage controlled current source. Okay, VCCS is. Now, what is the controlling voltage there in the MOSFET? Okay, since it's a VCCS, there has to be some voltage that is controlling the output current of the MOSFET. What is that controlling voltage? It would be better if you unmute and answer the questions, because I mean, typing in the chat has a lag, right? You'll probably be answering to one of my previous questions. My current question would be something different. So yes, please. What is the controlling voltage in the MOSFET?
Gate voltage.
Gate voltage. And why is that the case? What do we do with the help of the gate voltage there? If it's a controlling voltage, it should somehow be able to control it, right? You can unmute. I mean, there is nothing wrong even if you answer it wrong. All I want is you should attempt it. Okay, let's have a discussion on that one. So
Controlling voltage.
Yeah, controlling voltage. You mentioned that controlling voltage is the gate voltage there, right? Why not drain voltage there? If someone says you, why is not the drain voltage the controlling voltage here? How should your answer be to that query? Or in other words, if someone says that justify that the gate voltage is the controlling voltage in the MOSFET, how would you respond to that? Others, if anyone wants to comment on this one?
By controlling the gate voltage, the channel is formed in the between the terminal, like
correct,
MOSFET.
between source and drain. Yeah. So basically, I mean, we control the level of inversion in the channel using the gate voltage, right? Because your MOSFET is a FET, right? And FET is a field effect transistor. So there, that field effect action is controlled using the gate voltage, right? Now coming to, and what is the current? I mean, I said it's VCCS, right? What is the current source there? If this controlling voltage is the gate voltage, what is the controlled current there? Simple question.
Drain current.
Yeah, IDS. Now, for BGT, what is the controlling current? Because it's okay. This is a VCCS. This is current controlled current source, right? Unlike MOSFET, here controlling knob is the current. And that current is your input current, this one, IB. Okay. And what is the controlled current? Which current is getting controlled there?
Collector current.
Yeah, I see. Okay, so these are the pairs then. Now, is it same for both NPN as well as PNP?
Same, sir.
Same, right? For both the cases, IB is the controlling current and this IC is the current that is getting controlled. And what is the governing equation that relates these three currents?
IC is equal to beta times IB, and
Yeah, that
IC plus
is,
IB is equal to IE.
yeah, IE is sum of P plus IC. Correct. So yeah, fair then. And what is this beta factor called? What is this factor? Any name for
Gain.
this? Yeah, gain. Right. This basically relates your input current to the output current. Right. So this is current gain, you should say. Right? Okay. Let's move to another discussion. I said that this is current gain, right? Because I mean I have currents on both sides, right? Output current, input current. In general, this would have been something like this, right? I out is beta times I input. What if it would have been something like this? Mm, yeah, I out is suppose delta times V in. Which kind of gain would have been this? I mean, this is gain, right? Because this is relating output to input. But if I change this to say, suppose V input, I said that this is current gain. What about this?
One is
But I
current
have,
gain and another one is voltage gain.
no, this is not voltage gain. Had this been V out, then this would have been a voltage gain. But this is current relating to voltage. You would see such examples.
Transconductance.
Correct. Very nice. So this is transconductance gain. Okay. This is your current gain, this is transient, and that voltage gain is simple, right? V out is, let's say, some factor times V in. That would have been your voltage gain. Now let's move on to the third one, right? A technician uses multimeters, this diode check function, to identify the terminals on a BJT. There are only two places where a non-infinite reading is obtained, and they are as follows, right? From these measurements, can you determine? I mean, are you able to get it? I mean, this is your BJT. I mean, have you seen BJT in lab? Anyone done lab? This is how you
Yes, sir.
get there, right? I mean, you would have probably used BJT on the breadboard, right? So this is the BJT. You have three terminals, right? From these measurements, you need to determine what type of BJT this is. Is it PNP? Is it NPN? And also identify all the terminals. We say you didn't know which is emitter, which is collector, which is base, right? You put these two, you measure this reading. You measure across this and this, you get reading this, right? So based on this, can you determine, first of all, the nature of the BGT? If it's PNP or NPN? If so, how? And then go on and identify all the three terminals. Are you able to understand the application of this experiment, right? Given a random, say, suppose BGT device, you would be able to at least infer what nature is of that BGT and what are all the terminals. And we can label them using this experiment. So yeah, please. What is the type? do this as a homework then. Okay. So turns out your type would be PNP, right? And I mean, obviously, then your terminals would be what? Your terminals would be, if I label them, let this be suppose this is 1, this is 2, this is 3. This is your emitter. This is your collector. And this is your base. Okay. This is what you have to, do as a homework, how this comes up. It's not that difficult. Can move on to the next question. NPN transistor is connected as shown in the figure. What is the mode of the operation? So this is an NPN, right? NPN. What about this junction? Is this getting forward bias or reverse bias?
Forward.
Forward, sure. We're applying a higher voltage at N, right? It won't be forward bias, right? Do you agree?
Yes, sir.
So this would be reverse bias, right? This would be reverse bias.
PN junction would be forward bias.
Yeah, this one would be forward bias. So now, the question, which mode of operation is this?
Forward active.
Forward active, correct. Because our emitter base junction, that is forward bias, right? And collector base junction, that is reverse bias. Is everyone able to follow? Okay. This one is the forward active one. And basically, this is used as an amplifier in that mode of operation, right? So now let's move on to the next one. What about this one? A beginning electronics student, he is just learning about transistors, right? And he reads in the textbook that a bipolar transistor, either NPN or PNP, can be thought of as two diodes connected back to back, right? So he's being told that this is equivalent to, if I model this using these two diodes, NP and PN in series. Okay. So he's being told that this particular symbol is equivalent to these two diodes, right? P to N, P to N. Okay. Now acting on this idea, what the student does is he proceeds to connect two rectifying diodes, right? He takes this 1N4001 rectifying diode, he connects them back to back, and then he tries to use it as a transistor. But this idea does not work, right? Although the diode pair reads the same pattern of continuity as a transistor would, it does not amplify. Can you explain why?
Due to doping levels, the first diode would not allow current, even though second diode is forward biased.
Okay. Can you precisely tell which one? I mean,
That
label it.
right one is forward biased,
Right one is
right one
forward
is
bias.
and left one is reverse biased.
Okay.
But in case of actual BJT,
Uh-huh.
it will allow current due to minority charge carriers. But in this case, doping levels both three NPNs are. But in BJT, that would be
What
different.
what you're trying to perhaps say is that emitter and collector are doped same in this case,
Um, uh, yes,
right?
sir.
Which is not the case in BJT,
Yes, sir.
right? Anyone else who wants to
Uh,
comment,
yes,
or how many of you agree with this?
I agree.
Okay, one vote. What about others? I mean, others have been silent throughout the meeting. What he's saying is that in my BJT, uh, emitter and collector, they are not doped in the same level, right? Although they have same nature, right? Here both being N, but they are not doped in the same level. But when the student used this configuration, right, he took these two diodes, connected them back to back. Uh, the reason why it did not amplify was because in diode, this N and N had same doping levels. Are others able to get it? I'm hardly got any interaction or any response from others. I guess 2 to 3 students are responding. Uh, so yes, I mean, as he pointed out, the mistake is assuming that BJT is electrical equivalent to two ordinary diodes. It only looks like two diodes when it's tested for junction continuity, right? Uh, when base emitter junction is forward biased, your electrons they would inject from emitter to base, right? And the base is deliberately made very thin, right, and lightly doped. So most of those electrons they do not combine in the base, right? They what they do is they diffuse across it and reach the reverse bias collector junction, whose electric field sweeps them into the collector. So if we compare that to the case of the diode, although the junction pattern resembles, right, N, P, N, the two semiconductor junctions, they are physically separate, right? Between them are diode contacts, isn't it? Right? Metal leads, wire, etc. So electrons that are injected through first diode, therefore they cannot diffuse through a thin semiconductor base into the second diode, right? So the second diode knows essentially nothing about the carrier injection that is occurring in the first one. With one junction forward bias and the other junction reverse biased, the other one, I mean the reverse biased diode, it simply carries approximately that tiny leakage current in the reverse bias, right? Reverse saturation current. So the diode test works because BGT contains two PN junctions, but amplification is something that requires those two junctions to be coupled within one continuous semiconductor structure, right? By using a lightly doped base, right? Which we cannot do using this typical structure, right? So two discrete diodes, they reproduce the junction polarities, but not the physics of BJT, right? So we are done with this. If we should answer this one is, we will answer this in one line that mistake is assuming BJT is electrically equivalent to two ordinary diodes, right? Let's move on to the next one now. Now, the base current IB is always the,
Smallest.
yeah, it's the smallest one. So next one, beta for an NPN transistor is 60. What would be the alpha for the same transistor? Anyone? I would like if the students that have been silent so far,
0.983.
they answer it. 0.983. And how is that the case?
Beta by 1 plus beta.
Beta by 1 plus beta. Correct. And that is around 60 by 61, right? That is 0.983, right? How is that alpha equal to beta by beta plus 1? Right? You said that alpha is beta by beta plus 1. This would have been taught in the course itself. But how does this come about? Any idea? What is your alpha by definition? What is alpha equal to? Alpha is equal to IC by what? No, not IB, IE, right? You're probably answering for beta. Beta is IC by IB, correct? And we know, we already wrote that equation, right? That your IE is what? IC plus IB, right? Now, I can write this as follows. IC is what? Beta times IB, isn't it? From this one. If I use this here, what will I get? IE is beta times IB plus IB, which is nothing but IE is beta plus 1 times IB, right? Is it? Now, what is alpha? Alpha is IC by IE, right? And my IC, what would be my this IE from here? It would be alpha by, sorry, IC by alpha, right? IC by alpha is beta plus 1 times IB, right? And then I can bring this beta here. IC by beta, IC by IB is beta, right? So this would be what? This would be beta by alpha is beta plus 1, or I can say alpha is beta by beta plus 1. Is this clear? Any doubts? So this is how it comes about, right? I mean, no need to remember formulas. I mean, although you can, because it saves time, but yeah. And in fact, what if I would have given you alpha, right? And I would have told you that compute beta. Do you know that formula? Beta in terms of alpha? What is the formula for that one? Given an alpha, how do you compute beta? That alpha by 1 minus alpha, right? Is this clear, or should I show proof for this? Or is this trivial? Why am I not getting answers now? Anyone? Am I audible?
Yes, sir.
Okay, am I audible? So should I show the proof for this one? Beta, how this is equal to alpha by 1 minus alpha? Or can you
No
do this as
needs.
a homework? You can do this as a homework, right? Simple rearrangement. Now, yeah, let's move on to the next one then. Okay. So base width modulation, it occurs in BGT operation in which of these operations? Anyone? When will the base width modulation occur in a BGT? Will be this one, right? Forward active. Why? Because in forward active region, your base emitter junction, that is forward bias, right? And your base collector junction, that is reverse bias, right? And rest is simple then to induce, right? So now, ninth one, right? 9A in fact. You need to evaluate IC and RC in this one. You can assume beta to be this. Okay. So how should we go about this one? Anyone? Venkatesh, you? Sorry, Venkata.
0.986 milliamperes.
0.98. I guess you're probably referring to this one.
Yes, sir.
Okay. And RC Is RC coming this? See, for others, okay. Yeah, IE is 1 million. Is it?
Yes, sir. 3.04.
Yeah, 3.04. Now let me work. Let me work through the solution. Okay. So your IE is 1 million, right? Because this fixes it, right? And given your beta is 75, how much should be your IC? IC would be, let's go through this. We have IE as IC plus IB, right? And IC is beta times IB. Yeah, so my IE will be beta plus 1 times IB. From this one, I can obtain IB, right? How much is IB? Right, because I know this one, right? I know beta, I know this. The only unknown is IB. And IB comes about as 13.616 micron. Okay, and verify it at your own end. And IC is how much? Beta by beta plus 1 times IE, right? Which is 75 by 76 of what? This would be 0.987 million, right? And now the voltage across RC, how much is the voltage across RC? Let me write that by VRC. That is 3 volts, right? Yes. Now, RC is how much? 3 by current flowing. And current flowing is the collector current, right? And that we already computed, right? 0.987 milliamp. This comes about as 3.04 kilo ohm. Is this clear with everyone now? So that is why your option A is right. Now 9B. What about this one? Assume a silicon BGT. What will be the IC and RC for this case? Anyone? No? How much is I fixed in this case? 1 million, okay. Right? And IE is what? IB plus IC, right? And my IC, that is alpha times I, but alpha can be written in terms of beta. That can be written as beta by beta plus 1 times I. Right? Take beta, the one that we used previously, right? If you use 75 there, your IC would be how much? 0.987 milliamps. Right? Now, your collector voltage is specified as 2 volts. Right? The voltage across RC is therefore again 3 volts, right? VRC is 3 volts. It's the same question, I guess. Isn't it? It is same. Let's move to the next one. What about this? If you assume beta
Sir,
is
in
70.
Sir?
Any query?
In that question, beta didn't give an answer. In
In this
9B,
question?
beta,
9B.
beta, they didn't give an answer.
Yeah. It's actually the same question as 9A, in fact. I just realized. Right.
I think we have to proceed with IB is equal to IC
Maybe.
power of VBE, like that.
This one?
We have to proceed like IB is equal
Okay.
to
Okay.
reverse current into e power of minus, like that.
We can proceed like that.
If
Do
we
that
proceed
and
like that means we may get a different answer.
we might. Let's try then.
Get okay, sir.
I'll need to then obtain IC without using this one, right? What should be my IC? Now, this is an NPN one, right? Yeah. Right, the symbol ensures that this is an NPN one. Right, my IC would be less than what? I, right, which is 1 million. So my IC would be less than 1 million. This much is clear. I discard these two options. I'm left with 2. Right. And
We may get option C, sir.
we make it option.
Like if we see if we are eliminating like option wise.
Yeah, that's what I'm
Because
trying to. I'm trying to discard the ones. I guess for this one, assume beta is 70. There is some issue with this one. Huh?
Sir, we can apply voltage like V is equal to IR rule over there.
Where?
Like across the RC, as we got IC like less than 1 mA, the voltage like difference is 3.
But issue is we did not get it precisely, right?
Like we can just get it.
We can still get. We can still get some estimate. We can get in upper bound on RC. That is perhaps what you are trying to say. But let's try that. So if VRC, VRC is for sure how much? 3 volt, right? There is no ambiguity in that. IC is less than 1 milliamp. RC is how much? VRC by IC, right? Now, for upper bound, what I'll do is I'll take IC as 1 milliamp. That would in fact set a minimum bound on this one. Want it? Upper bound on the denominator.
Sir, or else we can try that options, right? So
Which one?
like 0.987 is there. If we try, are we getting the same volts across it, like resistor across it using this formula?
The issue is, I mean, we are not able to precisely obtain IC for this one, right?
So we can like try and error like using that options, right? So the given options, there are two options which are left
I
over
guess you try it out. I'm pretty much sure.
Okay,
I mean, they would have taken care of this one. If you use either that one or this one, they both would be consistent. That much I'm sure. Try this out. Let me know.
there. Okay, so
Use IC as 0.946 milliamps and then see is RC coming out as 4.18 kilo. It should, right? You are reducing I, R is getting increased. Perhaps. Did anyone try it?
sir, for that A option it is coming correct, sir. But for D option it is like resistor is 3.17 kilo ohm something.
Okay. Then this is for sure wrong. Then we are left with only one, right? So option A is the correct one. But we are done with this one, right? So now this one, right? Question number 10. Suppose you're not given VC. I mean, you need to find VC. Assume beta is 75. Solve this question. Oh, sorry. We got some disconnected. Just a second. I'll share the screen again. This one, right? So how much is VC? We will assume that VBE is 0.7 volt, right? And obviously beta is 75. Now, since your IC is what? Beta times IB. So that is 75 times IB. IE would be 76 IB, right? Because it's IC plus IB. So the current through this 10 kilo ohm resistor, it's not just IC. At the collector node, it supplies both, I mean, IC as well as IB. So I 10 kilo, that would be IC plus IB, right? And yeah, and that is 76 times IB. So your VC would be how much? 5 minus IR. I is 76 IB times R, 10 kilo. Okay, and let's mark this one. Similarly, at emitter, your VE would be IE times 2 kilo, right, which is 76 IB times 2 kilo. Correct. Likewise, so now if V is this one, what would be VB? We already said that we'll assume this one, right? Your VBE is 0.7. So VB is VE plus 0.7, which is this particular quantity plus 0.7, obviously. You'll have to write it again. So what about across that 20 kilo ohm resistor? Across that 20 kilo ohm base resistor, my VC minus VB, that would be 20 kilo ohm IB. Correct. And if I substitute, this would be 5 minus, let me write it. Let's use a different page, or perhaps use this page. If I substitute, then I'll get 5 minus 76 IB 10 kilo ohm minus 76 IB 2 kilo ohm plus 0.7, that is 20 kilo IB. On rearranging, this would be 4.3 IB 760K 152K plus 20K, right? And the IB, that would be 4.3 by 932,000. I mean, approximately this is how much? This is around 4.61 microns. Yeah. So your VC, that would be 5 minus 76 times 4.61 micro times 10 kilo. Right, evaluate this, that should be the VC, right? How much is VC?
1.49.
1.49. Okay, 1.49. So that's done. So any questions? If not, then thank you and see you in the next session. Okay. Yeah, for the week 1 session, I tried to record that and upload on the channel within 2 days, I would say. Okay. And anyways, we have a session on Sunday as well. That will be busy 3 days. Also, just a second. You can check this one, okay? This is where I would be uploading. I mean, this is a channel link, or maybe I can post the channel link here. So now I can do that. And this is my YouTube handle. Okay. I'll be posting the recordings there, and you'll have recorded meeting of today's session in that. All right. See you. Bye.